In the previous video, we've seen an example of intraspecific density-dependent competition for interference. Some of these cases is when there is a cruel fight among individuals of the same population for access to the reproductive females, for instance, like here, the elephant seals and Año Nuevo, just around the corner. This is a case in which individuals, contact and fight among each other, so push, other out of their own territory. There is another type of competition, which is typical, for instance, of filtrators like mussels in this video, which really suck up resources that are present in the water column to the point to clean it up and reduces the per capita amount of resources, not because they fight with each other, but they all consume that resources that are available. So this is a form of exploitative competition. It's a competition for shared resources that are in limited supply. It does not necessarily involve that competitors, even meet each other, so they can just be adjacent to each other, but they really affect the abundance of resources that is available for each individual. Let's look how we can represent this, with the mathematical formulation. What we have here in continuous time is the n over dt, so the rate of change of the population over time, as a parameter here, which represents the mortality basically by starvation. So it's a constant rate. If there are no resources, this population is going to get extinct in a certain amount of time, depending upon the values of mortality rate. But then there is a gain, a term here, psi of E, which is the per capita gain for each individual, which depend upon the amount of resources that are available. E is the portion of the common food resources that are ingested per unit time. Psi, which should actually be the small psi, is the per capita gain that is increased fecundity or decreased mortality that is obtained through the ingestion of a portion E of their resources. There are several functional forms for that, but we can assume that psi is an increasing fraction of the resources, the per capita portion of ingested resources. For instance, in this simple case, psi of E is equal to eta times E. Now, there are at least two different cases that we can use to basically represent this competition for the common pool of resources. The first one is the reservoir of shared resources. This is typical of filtrators like clam and mussels, we just saw the video, exploiting a resource that is distributed in the water column with a concentration C. Let's see what are the assumptions. The assumption is that the per capita portion of resources E is proportional, in this specific case, is linearly proportional to the concentration of the resource in the water column, and F is a filtration rate. On the other hand, the concentration C is a function of population density N, and we can consider a number of different cases, and here, for educational purpose, I want to show you at least two of them. In this first case, you see here the equation, which basically represent how the concentration C is a linear decreasing function of the density of individual N. And I didn't draw that on purpose to let you draw it, and so this is an exercise for you. The other case, which is represented here, in which this is still a decreasing function of N, but this is an hyperbolic function. So please go ahead and draw this function qualitatively for n equals 0 to large values of n on these two different cases. So a linearly decreasing case that is represented here, and this is the hyperbolic case. So we said that dn over dt is equal minus mu n plus psi of E of n, where psi of E is a linear function of E, the per capita resources ingested. Now we solve the two different models in parallel, basically. So the left screen with the blue background for the linearly decreasing functions, and the right one would be, for the hyperbolic function. Here we said that E is equal to C0 minus gamma n. So the per capita amount of resources available is a linearly decreasing function of n. And actually, eventually that portion goes to 0 when n is sufficiently high. And I'd like to compute that specific value. So we can rearrange the terms here. And as you can see here, there is this term here, which is a linear term of n, which is a combination of this model parameter. And then here we have a square terms of n. So this is nonlinear terms of n. Okay. So if we rearrange these, we can see that, we're going back to a logistic equation. This is very interesting. So the mechanisms that we described are completely different from the competition, for interference, where the individual actively move on the territory, they defend it, they push the other out, they fight, if necessary. And this model, in which we get passive, individuals that don't really move that much, if at all, and they just suck up energy in the water column, the resources, and the assumption lead basically to the same mathematical formulation. In the second case, we have a hyperbolic term here, okay, and this leads to the so-called Schooner model. It's an old model, it's still valid, in which we can still compute the the population density, the rate of growth of the population, a really low density. That's why it says n equal to 0, say n tend to 0. This is the rate of growth. And we can also easily compute analytically the current capacity K. And, for basically these, two models, you can now use the R script to describe the dynamic through time and see, for instance, where the inflection point is for the logistic model. We know that it's half the carrying capacity, or for the Schooner model. Note that for in the first case, so let's go back actually here. So what we see here is that the rate of growth of the population, a really low density, is the same for the two models, right? Eta FC0 minus mu, both for the Schooner model and the logistic model. Okay. So this basically means that the population growth is viable only if R at low density is larger than 0. And so this relationship can be rewritten in this way, and we basically see that the density of the resources in the outputs of individuals need to be at least to a certain level, that means to exceed, the value here for the population to persist. Otherwise, the population is not even able to persist. Okay. The Schooner model exhibits a sigmoid growth, but the inflection point occurs at density that are smaller than half the carrying capacity. So basically, therefore, the effects of density are perceived at lower density than in the case of the logistic model. In both cases, both K and R are increasing functions of C0. So if we increment the abundance of resources, the background where they're not consumed, we will increase both K and, the long-term carrying capacity, and as well as the R, for n that tends to 0, that just means the rate of growth of the population at low density. Now let's look at the second case, the one in which we have a resource flow. So it's still exploitative competition, but in this case, the resource does not need to be actively filtered or searched for, but it is immediately available, which is the typical case of light for macroalgae. Think about kelp. Kelp can grow up to 60 centimeters per day. it makes a forest. And of course, the caplet is below might receive less light than the crop that grow faster up there. You know. So let's look at the definition and assumptions when we describe this. In this case, we say that I is the flow of energy, and we say that each individual in the population cannot use more than Emax. So this is the maximum quantity that is able to basically use or absorb, which is physiological basically limitation. It turned out that if N is smaller than the flow I divided by the maximum per capita portion of resources that an individual can absorb, that means there is an abundance of resources. Each individual uses all the energy that it can absorb, and the population basically grows in a Malthusian way, which is described here. So this is the classic case, and you can see here the derivation. Basically, we got that the basic equation can be rewritten by putting eta Emax, and so we can gather the terms, and this is the classic Malthusian growth of the population. But what happened when the number of individuals exceed I divided by Emax? Okay, so in this case, there are not enough resources for every individual in the population to get the maximum portion that would be able otherwise to absorb. So there are two cases here. There are very kind of other pillars of population ecology. There are two extreme cases, of course, lots of cases in which are a little bit more in the middle between the two of them. So in the first case, the strongest individuals eliminate in a series of contests the weaker one until exactly n divided, n equal to I by Emax individuals remain. Only I divided by Emax, because the others, they basically, it's like the ABBA song, the winners take it all and the others get nothing, basically. And in the opposite extreme, each individuals grab whatever it can, okay? And so the energy flow is partitional more or less equally among contestants, that the per capita portion of resources that is secured by each individual is roughly equal to I divided by n. That is the case, it's an equitable case. It's like, having, the proverbial cake, and if there are only few of us, we can, get a large slice of the cake, each of us, but there's a lot of people and we want to be equitable and everybody's going to take a list. We're going to cut it in smaller and smaller portions so everybody gets a smaller portion. So the first case is referred to in ecology as the case of, context competition. And the second case is the case of scramble competition that is reported here. So in the case of context competition, what you have, basically you have Malthusian growth until n is below E divided by Emax, and then the population level off and stop growing when you reach the maximum number of individuals that can absorb the maximum individual portion Emax. So I didn't draw it here because I'd like you to try to draw it either analytically looking this equation or by running simulation and basically implementing this model into R, Python, MATLAB, Excel, whatever you like. Okay, so this is the case of contest competition. In the case of scramble competition, what basically happens is that if n is smaller than I divided by Emax, then we have Malthusian growth. But when n exceeds I divided by Emax, this is what we get here. Even in this case, the population reach an equilibrium point, which we can compute by setting dn over dt equal to 0, and find that the number of individuals the equilibrium, which we define as k, the carrying capacity, is equal to eta I divided by mu. Okay, how this equilibrium point is reached, in time, well, this is a simulation that I let you to do, guys. Okay, and basically, We're going to move to the next topic in a moment. Thank you.